Hey all, back again. Managed to get some time to basically snap all these bolts that we were talking about in the previous video. And I've got a couple other little things to talk about as well. So first of all, snapped all the bolts with a good quality torque wrench, lubricated all the threads. Each pair, because I had two of each, I did one without a washer and one with a washer. For the normal style head bolts, the Land Rover flanged head bolts, I did not use a washer because of their larger surface area already. And you'll see the socket head cap screws are still there, and there's there's a reason for that, but I'll get to that. Whilst using the washer reduced the amount of torque or the setting on the torque wrench that was required to snap the bolt, that's to be expected because washers also act like a bearing. So when you're doing your bolts up and the thread is screwing in and the bolt's trying to get longer, you're getting a lot of friction on the surface, and as much as a washer doesn't just spin around like a bearing, it acts like a bit of a bearing and creates less head friction. And that's another reason why washers are really important, to use proper quality washers, because the torque difference was quite noticeable between not using a washer and using a washer. 20 or 30 foot-pounds different on all, like it was consistent throughout. So with the washer as the bolts would normally be installed, mind you, again, except for these ones which we went with as per Land Rover installation, you don't use a washer with the flanged head crown wheel bolts. So the M8 coarse thread, sorry, M10 coarse thread, 8.8, class 8.8, and I'll just give you the values with the washer because that's more sort of consistent. That was 70 foot-pounds to snap it. The grade 5, so this is back to 3/8 UNF. The grade 5, so that was 8.810. The grade 5 was the same, 70 foot-pounds to snap it, and that's on par with the specifications of what the tensile strength of those two bolts are. They're extremely similar, if not identical, specifications. So that's class 8.8 metric, grade 5 imperial or unified national series of bolts. The next was the grade 8, not class 8.8, not grade 8.8, but grade 8. That was 90 foot-pounds. Then we have the old school Land Rover crown wheel bolt which can be called a place bolt with that specific head. That was 100 foot-pound, 90 on the grade 8, 100 on the Land Rover, and this one was 140. Now that seems quite a big step up, but we do remember that we have no washer and they're a serrated head. So yes, they're a class 12.9, they're a high class or high specification bolt, but there is also some factor in of the friction that the head, especially a serrated head, even though the serrations are going in the direction or with the direction of fastening, they're more friction in the unfastening direction. They're ramped like a sawtooth that's running the sawtooth backwards when you're fastening it and then digging in for it to undo, but there's still friction there more so than a plain washer. But as per we expected, the better bolts were more, but it shows that this bolt. And the other thing too is when I hit 90 or on both of the grade 8 samples that I had, the same bolt, the torque. So the way I broke them, and again, this is not scientific. It's not a good way. It's what's available to me. It's not what you would do in any sort of real situation to test bolts, and that's why they're done a specific way, and there's standards for all this stuff. But when I would hit a torque setting and it would cam over on the torque wrench, I would have to go up 10 pounds so I just went 10, I went 60, 70, 80, 90, because anything in between, the friction that was already there was making the torque wrench cam over, so it wasn't worth trying to get a finer measurement. I didn't have the ability to measure more accurately than 10-pound jumps. So these two were at 90 and so 90, and then the next any rate value I give you for any of these, it reached that value, and then it wouldn't reach the next value, and it would just turn and turn and turn until it snapped. These two, after 90, took few turns to snap, and same sort of these ones. These ones took almost double the turns to tap. So these were 90 and then snapping. So probably torque wrench set at 100, and these were 100. So torque wrench set at 110, and I just gave the value that they actually made the torque wrench click and cam over to. But these, when I went up to 100, it took not much rotations for these two to snap. Whereas these two, it was like turn, turn, turn. I kept feeling it was going to go to 110. It didn't. But, that may say something about the quality of the bolt as well. I think it's a better indicator than anything, and that's just a bit of a gut feeling. These I haven't snapped because the one socket that I had, that even though it's a good quality socket at 140 foot-pounds on the torque wrench, it's only a 3/8 drive socket that I had, and I had adapter. I was worried about twisting the hex part of it out of it, and I didn't particularly want to do that. If I can grab a one-piece impact wrench style male hex drive socket in this size in a 1/2-inch drive for the big 1/2-inch torque wrench, I'll have a much better chance of snapping them. But these are going to easily be these, and that's from past experience when I've snapped good quality socket head cap screws. They really are up that top end of tensile strength. So that's good. It confirms to me that these are a good quality bolt. I certainly don't call them junk. I like the design and the principles behind it, and they're at least a grade 8 in strength. So that's equivalent to your metric class 10.9. And it's interesting that some people are swapping the flange head bolts out and class 12.9 bolts out for class 10.9, and apparently it's a junk or whatever. And so a bit of info there. Now the other thing that I remembered, ARP, if you've heard of them, and I mentioned them in my last video, they make high quality bolts for the auto industry, especially for like race industry, whether it's head stud bolts, conrod or connecting rod bolts. They make for everything, accessories and exhaust manifold bolts and a lot of things, but they're really well known in the industry for high quality stuff. They also make flywheel and ring and pinion bolts, and I just printed this out off the net. This is current for them. So this is their ring gear bolts, as the Americans call them, same as a crown wheel for English, mechanics. If you look at the head design, that's different to what mostly ARP do. So this is a genuine ARP bolt. It's 3/8 UNF, and this is what I would call the standard ARP head for a bolt. Now, this is a 12-point or double hex. They also make the same style head in a standard 6-point or single hex, which would be just your standard head like that, but it's still flanged with that outer flange. But the more point I'm making is the proportions of the head and the style of head, whether it's 6 or 12 point there, all of that is sort of like standard for ARP in that size, and for a lot of their bolt range. Now, if you look at that closely there, and you look at the head, it's a bigger overall diameter for the ratio of the thread or the diameter of the bolt. It's a bit thinner in proportion this way, and it's got this relief in the top. These bolts, this style of bolt is specific for ARP for their ring gear bolts, their flywheel bolts. There was one other application I can't remember, but I don't think that's a coincidence. I think they're going along the lines of a place bolt and creating a head that is a shock absorber for high shock or high impact loads. And it talks about here tremendous shock loads for drag racing and whatnot. The other thing that's interesting is their Pro Series is 190,000 PSI of tensile strength. That, just as a reminder, is greater than class 12.9. 12.9 is 180, so your socket head cap screws and these 12.9 flange bolts are 180,000 psi. So ARP don't make one alloy or one stainless. They make they have varying grades of material they use in their forgings, and they have various specifications for their different bolts in different applications. You can look at all this stuff online. If they don't have the information, you can email them. They're very, very helpful, and they'll give you really good accurate specs on their stuff. They are not messing around. Their QC and what they're doing is right up there. So just an interesting point that they choose a ring gear bolt with a head design that is, what I feel, especially with this relief in it, when you read about the idea of place bolts, that's heading down that path for sure. It's a bit hard to see. There's a little bit of a smooth shank there. They don't thread it all the way, and they're not saying, hey, we need to make this a softer bolt to shock load or whatever. Again, the only issue I have with ARP, unfortunately for us, the only 3/8 UNF ring gear bolt they make is 0.8 of an inch long, which is about 20 mil. I feel that's a little bit short, given that the carrier or hemisphere flange, that looks thicker there, but remember it's relieved. That's going to be 9 to 10 mil. And the crown wheel thickness is, and again, it doesn't look at there, but that's close to 15 mil. So there's your 25 mil. So I feel that and ARP don't make a Land Rover application, and that's not surprising. Land Rover would be 0.0001% of their client base, given the population of America and what they're gearing their stuff and vehicles and stuff they're gearing towards. Unfortunately for us, if that was a 1-inch bolt, or close to it, I'd be really interested. If that head fits in the relief here, I'd be happy to run that bolt. The only thing that holds me back is, unfortunately, the length of it in the ARP. I haven't contacted them yet to see if they offer another bolt that I haven't seen or found in the catalogue, something I could possibly do. At this stage, I'm still unsure what bolts I'm going to run. I'm possibly going to run these and cut them down. So that's an ARP bolt. That'll be 180,000 psi, so class 12.9 equivalent. And I'll be definitely running the ARP hardened washer. And another feature of the hardened washers that's a bevel relief you can see there. And the reason being is the ARP, and you won't see this on the phone, unfortunately, because it's not that great a camera. There's quite a generous radius between the shank and the head, which is a great structural stress design. That's really good. And the washer is to make sure that radius doesn't get bound up on anything, and that's really crucial with good quality bolts. Interestingly enough, that's the opposite. That's like an external radius, whereas the good old Land Rover ring gear bolt or crown wheel bolt actually has a relief in there as per the place bolt design. So possibly I might run these. I've got plenty of these. I'd probably be pretty happy running those. I'd run those before I went and just bought a grade 8 bolt. I'd run those before I ran these bolts. I'm just not a fan of the quality, and the other thing is these are shorter. Even though, yes, they did break under my crude test higher, it's still just a bit, I'm not sure about them. But it's just information. I'm just passing on a bit of information that I'm gathering. Talking of installing the ring gear on the carrier, the first thing that's important, and this goes with anything mechanical if you're trying to do good work, is clean, and not just clean components and absolutely clean threads, and run a good quality new or very good quality bolt that's in great condition through your threads by hand, and make sure that you haven't halfway through that feels a bit iffy, because then you need to investigate and make sure your threads aren't, because that'll be an issue for clamping force, and there's already potential distortion in your female thread in your ring gear that could lead to problems. So the other thing is these surfaces here. So especially around the holes, make sure there's no burrs or dags, but all the way around, make sure it's nice and flat and there's no raised burrs anywhere at all. and same on the back of the crown wheel. No burrs around the hole, no burrs or dags around the edges here. Really, 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 really clean. And you know, again, these have got a bit of oil residue and everything on just to stop the rust living here in southeast Queensland. You know, clean with your acetone or your parts cleaner or your brake cleaner, super, super clean, because the best for the friction, which we're, you know, we're getting the clamping force from the bolts to create that friction of those two surfaces. The best thing we can have is perfectly flat surfaces that are parallel and mating, clean, 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 and no little dags are going to hold it off and then get crushed, create imperfections in the material. We want that flat. We want as much surface area from the crown wheel in contact with the flange of the carrier or hemisphere to create as much friction as possible with the proper clamping load of the bolt. So that's really important. If I slip this on here, if I slip the ring gear, it'll only come down so far. It won't go all the way down. And this is one-handed, it's not great because I'm going to get it cockeyed. And the reason being, and this is standard, this is not a maxi drive thing or an Ashcroft thing, this is standard for all ring gears. The last bit of the hemisphere is a little bit bigger. It's an interference fit between the ring gear and again, that still hasn't gone all the way down. It's that last bit, which is the height of the ring gear. They're an interference fit, so you know it's not going to just drop on there. It's really well located and not going to move around. You can heat the ring gear up, and it won't take a hell of a lot. It won't take hundreds of degrees, maybe 100. You know, 70 degrees probably get it there. You can do that with an electric heat gun, like a mechanic's hairdryer. You can put it in an oven and get it warm. Yeah, you could put this in the freezer to cool it down and shrink it. I don't think that's necessary. I don't particularly like doing that. It just forms a lot of condensation. Structurally, I don't think there's anything wrong with it. I just, you know, if I'm not putting crazy heat into things, it's okay. Once you've got it on there, you really want to make sure. I had to take it off with two hands. So I had to put the phone down. So when you have the ring gear on there and you get it on there, you really want to make sure, because there's a little bit of play in all these holes, and that's how they're designed. I'm not having to press that bolt through there. A little wiggle room, tiny bit of wiggle room. You want to make sure that all the holes in the ring gear are as centralised as possible, because you don't want the bolt rubbing down the side of this hole and creating more friction, which may give you a false reading when you are doing your installation torque, but it also can create binding and want to cock the bolt over on an angle, which is not good. So when you're getting it on there, especially if the interference fit is a bit tighter than loose, you know, you really want to eyeball that for as centralised as possible on all those holes. So super clean threads, clean surfaces, clean dry surfaces, no oil or anything like that, and you know, get the two together. Personally, what I would do once I've got all that and I'm installing the bolts, I'd put all the bolts in finger tight, clean, dry bolts. I would torque the bolts up. So let's say it's 40. Well, the factory manual says about 42 foot-pound. So I would personally torque them up to say 30. Now that's 42 foot-pound lubricated, okay? So if you were to do it dry, it would be higher torque reading because there's more friction there on a dry lube to overcome in the thread to create the same clamping force. So, and the reason why I'm saying install them dry with nothing on is because what we want to do is we want to pull the ring gear and get all this clamped under load. You don't want to have it sitting there and go, okay, I'm going to Loctite each one up, because there's time in that, the Loctite, because you want to get all these, in my opinion, you want to get them all on finger tight, so they're all sort of same, nip them all up the same, and then torque them up to say 30. And this is my way of doing it. You know, if you see something screamingly wrong with it, please comment. The lubricated final torque setting is going to be say 42 if we're using a factory Land Rover crown wheel bolt, and we'll just use that as an example. So okay, so I will dry a clean, dry bolt with washer whatever. They're all in. I'm going to go up to 30 and I'll do opposite. So I'll go from there to there, to there, to there, to there, to there, to there, and so on, right? Not just bang, 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 because I want to pull the ring gear as square as possible. If we go around in a circle, we might start to sort of cant it or whatever. So opposite within reason, because if you keep going opposite, you're just going to go back and forth, and that doesn't achieve anything. So go around in a star pattern or opposite, whatever you want to call it. And you might do that and then back them off a little bit and then do them again. And you just, seating the ring gear properly. Now, you're not going to the full torque, and you're certainly not going to the full torque, but not only numerically are we not going to 42, we're only going to 30, but we're doing dry. And the reason I'm saying dry is we can't put the Loctite in at this stage, and I'll get to that, but you don't want to put oil in there, because then you're going to have to clean all that out again. So if you've done all this cleaning prep, so say pull them up to 30, and then when you're happy that it's all seated really well and that you've done that once or twice, then I would loosen one, take it out, Loctite it, install it. So we've still got this really good clamping force everywhere else. And then if you want to, you can have a little paint marker and put a dab of paint on that bolt so you don't have to remember which one you've done by memory, because you might turn this a bit or whatever. It's easy to forget. A little paint pen, white, yellow, red, whatever colour tickles your fancy. Just put a little dollop of paint and then, or a bit of chalk, whatever, but just so you know. And then you'll go to the opposite one and you'll remove that, Loctite, install it, correct to the correct torque. So now 42, and then bang, bang, bang. So you've got all this nice tension, equal tension or close to, and then you're not under the stress of having, like you pull this one up tight, but you haven't got any other bolts in, you've just got the ring gear there and you torque it off and your Loctite's there. The ring gear hasn't seated properly, and we're talking about something you can't see, but it's certainly there. So that's how I would install the ring gear. Clean, 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 clean in here as well, and clean on the diameter of the hemisphere, the mating diameter of the hemisphere. Once you've done that, you can go around then, even with them penned, you can go around and then go in this direction and just check every single one for a second time that it's still hitting the torque on your torque wrench, and you've achieved that. So bit of information on the bolts, bit of information about ARP bolts, and they're a specialised ring gear bolt. Hopefully this will all edit together okay. Still having problems with the phone, no surprises there. The other thing I wanted to touch on, given we're talking diffs and we've gone through about the information about bolts in general and bolts for the crown wheel, the other thing that I'm seeing getting changed in the diff centres, so we've got our cast iron housing here, whether you call it a third member or a carrier housing, this being the carrier. The bolts in these, which are class 8.8 from factory, I'm seeing these getting changed for socket head cap screws, again this type, but in this size and thread type. The reason why that's another sort of poses questions for me is that they're going from 8.8, class 8.8, to straight to 12.9. So that's a big jump in tensile strength. And what I wonder and I'm asking is, first of all, what torque specification are they installing these new socket head cap screws to? Reason being, if they're only torquing the bolt on installation to the same value as per the workshop manual, and I'm going to take a guess here from memory, I think it's 90 Newton meters. Regardless, if they're doing it the same as the workshop manual, they are not getting any more clamping force at the carrier cap. So what are they achieving? And I'm not saying they are. I don't know what torque they're getting spec'd to, but it's the question I'm asking. So if they're not torquing the new socket head cap screw to a higher value, they aren't achieving anything as far as clamping load goes. Okay, so the question or the statement then becomes, but it's a better quality bolt. Well, it's certainly a higher strength bolt. We know that. And quality, you would assume if they're getting a good known brand, not a problem. The reason I have concern about that, if they are talking them to workshop manual specifications, is we go back to the study and the example of under tightening the bolt. The joint and the forces it sees determines the clamping force required. The engineers have figured all that out, and they've used the bolt specification that gets that clamping torque and is also within the range of the correct preload, which is the tightening of the bolt itself. If the bolt is not tightened to the correct preload for the bolt, regardless of the correct clamping force, then, and it's under tightened, we go back to the example of the test where they have high tensile, high quality bolt, 180,000 PSI tensile strength, ultimate tensile strength. It was tightened to 40% of that tensile strength. It was cycled in a specific machine with a specific weight to mimic fatigue cycling. It managed 6,000 cycles before it broke and failed. They use an identical bolt, the same machine, everything, all the parameters except for they then tighten that identical bolt to 75% of the ultimate tensile strength. Cycle it in the same machine with the same parameters and everything, and it did 6 million cycles before fatigue because the bolt was in the correct range of preload or pre-tension. So that's the question. Are we tightening these new socket head cap screws to a higher value, which is increasing the clamping load on the cap, which could be a good thing, and is the right spec for the bolt? The next question that comes from that, if you're increasing the torque value and the clamping load, this is cast iron. It's not mild steel, it's not cast steel, it's not chromoly steel. There is a limit to what this can have as far as what the threads will hold. So the cast iron is soft, it's like aluminium. If you've ever worked with aluminium or if you've worked with cast iron and you drill it, you'll notice how soft it is compared to even mild steel and how easily it drills and taps. And that's why in a soft material they use a coarse thread. Aluminium and cast iron, they'll use a coarse thread because they get more surface area on each thread to engage in the softer material. This here will be a case hardened high quality material for specifically ideal for gears. This will be a different material to say an axle shaft material most probably, and these will absolutely have no problem holding a fine thread, and a fine thread is desirable in this sort of thing, this application. That's one thing, and I'm not saying they're doing anything wrong or bad. I'm asking the question because there's things there. All good intentions and thinking, right, we don't know how much this bolt's been used and fatigued, we want to throw it away and replace it with a good bolt. We know socket head cap screws are good quality bolts. The question becomes, is it the right bolt for that application, or the right class, strength or grade of bolt for that application? Can it be applied? Does it give us the benefit? Unfortunately, I can't answer that for you. I think an engineer would know some basic numbers based on cast iron. I believe it's nodular cast iron. So then again, like all materials, aluminium, steels, cast irons, there's not one grade, there's multiple different grades. Grey cast iron being sort of the crappy sort of bottom of the range stuff, and the nodular being better. I think this is nodular cast iron or an SG cast iron, which is vastly superior to a grey. It's an M12 coarse thread, and I believe we've got 2 times the diameter there, so maybe an engineer could figure out what that thread will safely hold without fatiguing and going to yield or failing. And then once we know that, we could confidently say, okay, well, we can upgrade the bolt and torque it to a higher spec. I am uncertain about putting a better or higher strength bolt in this application and only torquing it to workshop manual specifications. I think that's potential for problem. Again, if you're an engineer and you can add something in there and say why, yes or no, great, please do. So, we've covered the bolts, the crown ball bolt specifically, some basic bolt tech, some good quality aftermarket bolts, and some various things there. I've probably offered more questions than answers, but sometimes that's the start of doing things in a better practice or, to the best of our ability. So feel free to comment and add information or links to any studies or anything, SAE studies or papers that, or text, that'd be unreal. and hopefully you've taken something for this and you can potentially apply it to your Land Rovers in general, and food for thought when doing your bolts up, especially all the structural bolts on axle housings and the differentials and the mechanical members. So appreciate the time to watch it if you've got through it all, and always happy to have a comment, positive or negative or criticism, not a problem. And yeah, good luck and thanks for watching. Cheers.